A storm is coming! I don't want to read this all to you guys, but I need to point out a couple things within the word problem that's happening here. Now, there's a bunch of words up here, and it's going to give you a context as to how to, or what's going on in this problem. But when you read it, you got to look for clues that kind of tell you what like the math information is telling you. So like the first thing I saw when I read this was the word rate. Whenever you see the word rate in calculus, your ears should perk up because that is calculus. That's the big concept in calculus. And so when I read on, I see that this says meters per hour, and that is a rate unit. And so F right here is essentially a velocity function, or you can call it a slope function. That is the rate function in this context for this problem. I also like to circle numbers in the problem because usually those numbers mean something. T equals hours, it's important to know. And then when we read our first question, it says, what is the distance between the road and the edge of the water at the end of the storm? Now, the end of the storm would be at 5 hours. That's the end. That's what it says. It says that the storm ended at 5 hours. And so, distance. How are we going to find the distance with the information that we have in the problem? So I'm going to try to explain this by using the units, okay? F is meters per hour. Now, if we were to take the derivative of a meters per hour with respect to the hours, which in this case is T, we would get meters per hour squared. And so that would be the units for our F prime right here. So this is F and this is F prime. If we were looking for meters, then that's going to require us to do an antiderivative. So an antiderivative of meters per hour would give us meters. Well, since we need distance, which is meters, we're going to take our meters per hour function and then do an antiderivative to find our answer. So as we answer A, I want you guys to think of meters per hour as being your F. F prime is meters per hour squared, and then capital F is going to be our meters, which is what we need. And so we're going to set up an integral. We're going to take the integral of f of t dt to find capital F. This is going to be our capital F function. Now, the integral right here, the limits are going to be our time because that's what we're plugging into the function is time. So we have our beginning hour and our ending hour. We're going to plug in f of t. And I don't need to write out what f of t is because it's already defined for us earlier in the problem. And then I'm also going to need to add 35 because that's where we start. It says somewhere up here, 35 meters. It says 35 meters is where we start. And then when we add what the function does, whatever the function's result is, it can be positive, it can be negative. Most likely it's negative since the sand is wasting away. We have to have 35 plus this, and that'll give us the distance between the road and the edge at the end of the storm. Now, because this is a calculator problem, I want to give you guys some tips on using the calculator to solve something like this. First thing we're going to do is we're going to take our two functions, this function right here and this function right here, and we're going to plug them into our calculator. So to do that, press the y equals button or your function button if you don't have a TI, and carefully put in your two functions. I know this doesn't look exactly like your Texas Instruments, but here's your y equals button, and these are the two functions that I put them in. Take note of which y you put each of them into. I put my f function in y sub 1, and I put my f prime function in y sub 2. Now when I press second and then quit and get back to my home window, I can plug in the integral and get my answer. Now I did this twice just so you guys can see how important this is. When I did this one, I got 32. When I did this one, I got 26. The difference is, when I did this one, my calculator was in degrees, which is a big, big no-no. Before you even get into taking your exam, make sure your calculator is in radians. There's a really good chance you're not going to use degrees. I'm like 99.9% sure you're not going to use degrees. You're going to use radians. And so This is the correct answer right here. And if you got this because you left your calculator in degrees, oh well, you just got that easy problem wrong. So this is the correct answer, and so I'm going to go ahead and write that down. All right, we got 2.6494 meters. Now let's attack B. On B, it says using correct units. Oh, please make note of that. Using correct units, that's huge. It just told you how you're going to get one of the points. Using correct units, interpret what this thing means. And so when you interpret this, you have to know what the F prime means, you have to know what the 4 means, and you have to know what this number means. F prime is the rate of the rate, right? It's up here. This is your derivative of the rate. And so essentially you can call this acceleration. And then you have 4. 4, that's the value of t, so that's hours. So this is saying after 4 hours, this is your rate of the rate. This is the acceleration, okay? When I write my answer, this is what I'm going to say. I'm going to say after 4 hours, the rate that the distance is changing is increasing at a rate of 1.4004 meters per hour squared. Oh man, that's huge. So I would get a point for just writing meters per hour squared, and then the other point would come by me saying that the rate F is increasing. Okay, so that increasing word is huge. Now let's take a look at C. C is really complicated with the way it says it. At the time during the 5 hours of the storm was the distance, at what time during the 5 hours of the storm was the distance between the road and the edge of the water decreasing most rapidly? So it wants to know when distance, which is F right here, when is distance decreasing most rapidly? F, regular F, tells us what the slope of capital F is. So if F was positive, then capital F would be increasing. If F was negative, then capital F would be decreasing. If F was really negative, like it was a really negative number, like instead of -3, it was like -20, then F would be really steep at that moment. It would be decreasing most rapidly. And that's the key right there. We're trying to find out where F is decreasing most rapidly. So where do we have the most negative F? That can also be translated like this. Where is the minimum value of F? Oh man, this problem is so tricky. So you're trying to do the first derivative test on F so that you can see where capital F is steepest going down, like the function. So what we're going to do is we're going to do the first derivative test. We're going to use the derivative right here to find the critical values of F, and then we're going to plug those critical values back into F to find out where we have the most negative slope. And we can't forget to also plug in our endpoints. Whenever you're looking for an absolute minimum or an absolute maximum, not only do you have to plug in the critical values, but you also have to plug in the endpoints. So with the help of our calculator, I'm just going to take a look at the graphs and help you guys interpret what they mean so we can do the first derivative test. You can see here in the light blue curve, this is F prime. And then green right here, the green curve right there, that is F. Right now, I just want to look at F prime. So when I look at F prime, wherever the F prime is crossing the x-axis, those are our critical values. Because wherever F prime equals 0, that's where the critical values are of the function you're trying to find the max or min for. In your Texas Instrument, if you press second and then the calc button, which is one of the top buttons, you'll be able to tell the calculator to find the zeros of the function. With my calculator on my iPad, I was able to just touch where the x-intercept would be, right there and right there, to get my two x-intercepts, which you see right there. When you guys write those down, make sure you go 3 decimal places. So I'm first going to write down the x values for our critical points of f of t. And I get 0.662 and 2.84. And then what I need to do is I need to plug in like both my critical values and the endpoints and see what I get. Now check this out. Everything is already in your calculator, so it'll do all the work for you. This is how you put it in. Use your yvars button. You say vars, then go to function. And what you do is you take the y value, or the y right after y1, you plug in the number that you want to plug into. So these are my two critical values. Using parentheses, and then I press enter. I got -1 and -2. -2 right now is my lowest, my most negative slope. When I tried the y values, or the endpoints, I got a -2 and I got a -0.48. I'm gonna go ahead and write that down on my work right here. And when you do it, make sure you go to 3 decimal places at least. And in this one right here, this number is clearly where my minimum slope is. And so t would equal at 2 hours, 0.84. That's where you would get the most decreasing part of the function. That is the capital F, the distance. Okay, now let's do this last question. When you read this last question, I hope you saw the word rate. This right here represents a number, okay? G represents a number. What is that number? This number represents the rate that the sand is going back into, being pumped back into the beach, okay? And here's your units for the G. So G is the rate that the sand is getting put back onto the beach. And then the function, or the problem tells you, it defines what P is. P is the number of days, and so that's like T, but this time it's that they're using P because they can't use T. They already used it. The question says, write an equation, okay, so that's all we have to do. Write an equation involving an integral expression, okay, so we know we're going to have an integral, whose solution would give the number of days that the sand must be pumped to restore the original distance between the road and the edge of the water. This function represents rate, but we really need an amount. Like, we don't need the rate, we need the amount, not meters though. Right now we're working with, actually I stopped, sorry. We are working with meters, and the antiderivative of G will give you how many meters you're refilling per day. So first let's write an expression that would represent how many meters we lost. We lost from 0 to 5, we lost this many meters. Okay, I know this is a rate, but remember when we do the integral, it gives you meters, not a rate. Okay, now this is what we lost. We want to find out, or we want to finish our equation, like we want to write an expression that would give us how long it would take to get all the meters refilled, okay? So we're going to also take the integral from 0 to 5. I'm sorry, not 5. 0 to x, because that's the number we don't know. That's actually p. And then we're going to put g of p in here, dp. So x is the number of days that we're plugging into this function. And when we plug it into there, then it would eventually go in there after you take the antiderivative. Okay? Now we want to find out when this doesn't equal this, but equals the opposite of that. Why do we want it to equal the opposite? Because this alone, think of it, it's probably, it is. It's a negative number. So we want to make it positive, so we just throw a negative right there. When will the amount put back equal the amount that was lost? And that's the end of that FRQ.